Okay, I think the clock started running, which is kind of a signal that we can start. Hello, my name is Adam Warski. I come from nearby, from Warsaw in Poland. I work at Software Mill for like 16 years, which is a very nice number, of course. And for a long time, I've been trying to use functional programming and trying to understand what functional programming is. And I think I arrived at some kind of a conclusion, which I will try to share with you. So, of course, this question might seem trivial. Right, it might seem obvious what functional programming is, and obviously it's programming with functions. And this could be a very short talk then, but we will try to be a bit more elaborate. I think if you would go on the street and ask random people what is functional programming, you would actually probably get a couple of different answers, I guess. So I don't think it's that obvious what does it really mean, right? What does it mean to program with functions? Like, can I only use functions? Like, if I'm calling Java methods, is that functional programming? Or maybe there's something more to it. So also, like, what do people mean when they code in FP style? I think after some time, we have some feeling of what coding in FP style might mean. But it's sometimes hard to articulate. So let's try doing that. And before we start, just a very short personal history, like where is this coming from? So I've been doing functional programming during my university time, using OCaml and Scheme and other fun languages. Then I went to earn some money, and I started doing Java. But I came back to FP by starting to do Scala. So my first Scala code is from 2010, so that's like 15 years now, right? And there's actually one of the first commits. It's a function that's in the standard library, but I wasn't aware of that then, so I wrote my own, which is worse. So yes, I've been doing Scala for quite some time, and I think Scala is a very interesting case study when it comes to functional programming itself, because there was a lot of experiments into how you can actually blend functional programming, object-oriented programming, and there's been a couple of incarnations of frameworks, of approaches, which led us to discover what is really valuable in FP and what is maybe too much, right? So maybe some of you remember there was a very popular framework like 15 years ago called Lift. Then we moved over to Akka and Actors. Then we moved to like Monix, Cats Effects, which is like the peak of functionality, let's say, in Scala. Then maybe, we thought that it's too much, so we came back a bit to like direct style Scala. So it is kind of yet another incarnation of this graph where you start off doing like really simple like direct style code, then you try to be very smart and maybe create some things that are overly complex, and then you truly discover what this thing is all about. And hopefully we are approaching this downslope there right now. So in a way, Scala has been a proving ground with many potholes left of failed approaches. And it's kind of a similar story with object-oriented programming, right? There was a time where we, as a community, we have been discovering the limits of how far you can push object-oriented programming. And we kind of learned the hard way that maybe using inheritance everywhere and just overloading methods too much and so on isn't such a good idea. And it just results in code that's hard to read and hard to maintain and so on. So I guess we made a similar journey in function programming and in Scala in particular as well, to discover like which patterns are valuable and which are not so much. Yeah, so now we will actually start the main part of the talk. If you would have any questions, I will try to answer them at the end. So you can, go to that page and actually ask your questions. So please do that if anything comes up. Okay, so we will start with kind of a practical take. We will try to get a feeling, look at some code examples of what functional programming actually might be when you see it. So we'll try to take you know it when you see it approach. So and we'll see if it actually works or not. So yeah, there will be a mix of languages, so you may try to identify all of the languages that I've used here. So we have like 2 code snippets, right? And they do the same thing. And one of them is supposed, at least, to be more functional, right? So who would say, wait, we are on this. Who would say that the right one is the functional one? Not that many. And the left one? Yeah, I can see some hands up, right? Yeah, so like, if you ask a random programmer which is more functional, they would probably point at this one. So what makes it more functional, right? So we can kind of feel it, but what kind of characteristics is it? So first of all, we can see that the left-hand side code is more declarative, right? We declare that we have an array of numbers, and we want to transform it using a map, filter, reduce, which are function applications, right? So this fits nicely with the name. But we don't really say how these transformations work, right? That's the inner workings of the map, filter, and so on, as opposed to the right-hand side code, which is very explicit. It's imperative. It says exactly how this transformation is done. Also, I would argue that it's kind of more obvious what kind of transformation is happening to this collection using the declarative approach than the imperative one, right? You have kind of to parse a lot of code, like what do we do with those numbers, as opposed to this declarative snippet. So we've got a couple of function characteristics. We've got function application, which is a core characteristic of function programming. So what we do is we compose and apply functions, right? So we apply functions to some arguments. We compose functions, meaning we call the filter function on the result of the map function, and so on. So it's like a chain. On the other hand, in the imperative code, we've got explicit control flow methods, so loops, conditionals, and so on. Also here, you might notice that we are using higher order functions, meaning that some of our functions take other functions as arguments, as parameters, right? So the map takes a function as a parameter. So also something that signals that we might be using functional programming. So let's go a bit deeper into another pair of snippets. So once again, we have the same logic. We want to filter the menu either for vegetarian and non-vegetarian items. Actually here, if you are not vegetarian, you are obliged to eat meat, which might not be true in general, but it's code, so it contains bugs from time to time. So once again, the left-hand side version, would you say it's more functional than the right-hand side? Anybody? Or maybe the right-hand side is more functional? Some hands. So I guess the majority would say none, but okay, that's fine. So what is happening here is we have some condition on which we want to filter the menu. And in the left-hand side snippet, what we do is we call filter twice using some kind of predicate, right? And on the right-hand side version, we actually extract the predicate into a value. And that's also a characteristic of functional programming, is that we can capture functions as first-class values. And thanks to that, we can avoid the code duplication that we have on the left snippet, right? The left snippet needs to call the filter in both branches. And on the right-hand side, we can capture the predicate as a value, so the function as a value, and use it as a filter expression. We are also using if as an expression, right? So the if here has a value. So very often, for example, in Java, if is a statement. If some condition, you can do some actions as some other actions, right? But if overall, you cannot assign the result to a value. You can do it with the Elvis operator. That's why it's introduced. But if itself is a statement. And in functional programming languages, more often you have things that are expressions. OK, next snippet then. So here, again, same logic. We have some transformations. So we have a map from persons to addresses. And we have a Chris who, when Chris turns 30, he actually moves from Warsaw to Krakow. And we want to reflect this in our mapping, in our map. And we have two ways of doing that, right? On the left-hand side, on the left-hand side, we are using immutable data structures. So we have the person class and the address class that are both immutable, so you cannot change them after they are being constructed. We also have a map, which is also immutable, so we can only create copies of this data structure. We cannot modify this data structure in place. On the right-hand side, we are using mutable data structures. So we have a mutable person and address class. We are using a mutable hash map. By the way, on the right-hand side, we are using a mutable class as a key to a map, which is a very bad idea almost always. So, these are small code snippets, but we already have two bugs, which, happens in production as well, I guess. One more point for immutable data structures, that's simply not possible. But going back to functional programming, very often a characteristics of functional programming languages is that you are using immutable data for two reasons. First of all, notice that all of the methods, all of the functions that we are using here actually have meaningful return values, right? So the copying of the Chris instance so that the age is updated yields a new instance, right? So the copy has a meaningful value. So we have an expression which has some value. When updating the map, the friends map, by removing the old key and putting in the new key, we are also obtaining new instances of the map, right? So once again, these functions have meaningful return values. So we have expressions which have return values which we can then use as parameters for other function invocations. On the right-hand side, we are using mutable data structures, and we are mostly doing things just for side effects, right? We are updating the Chris instance with a new age using a setter. So this doesn't have a meaningful return value. It just returns void, right? Same with friends.put. We are just calling that for the side effects. And in general, limiting the side effects that our code has is something that's often encountered in functional programming languages. Okay, next snippets. These are not that obvious now. So we can now push the limiting of side effects into a limit and just say that you cannot do any side effects. Then all of your functions are pure, they are easy to understand, and whenever you want to actually do a side effect, you have to construct a data structure which describes what the effect does, right? So on the left-hand side, the first snippet, that's just normal imperative programming where we have a series of method invocations, and as soon as we invoke these methods, here it's like launching rockets, something that we do every day as programmers, of course. So as soon as you invoke those methods, these effects are actually run. So the middle snippet, that's Haskell, I guess. So in Haskell, you cannot really run any side effects. You only construct this IO data type, which describes what should be done when this computation description is being run, right? So just running this code will just create a data structure. And the syntax here looks very similar. This is a very simple case. We will see a more complicated one later on. But the real difference, like the real syntactic overhead of this approach where we create descriptions of side effects is when you have conditionals, when you have loops. You cannot just do that because you have to construct data structures which describe the condition, right? So you cannot just use if, you cannot just use a for, and so on. And then some languages, like the one on the right-hand side, that's Unison, a very interesting language, kind of an experimental one. They use abilities. So they say you can take both an imperative and a functional approach to them, but that's like kind of a side note. Yeah, so we've got this distinction that in functional programming languages, we often describe effects or concepts as values, and here we have immediate effects. Okay, the last but one code snippet where we will identify some characteristics of FP. So here we've got a snippet where we parse some request. On the left-hand side, the parsing of the request might throw an exception because the request might be invalid. Then we validate the order. Once again, this might throw an exception. We then, do some calculations on the order. Maybe we apply a discount if the customer is loyal. And finally, we create an invoice. Okay, so that's a very imperative way of doing things. Probably quite clear to read. Might throw some exceptions. And yeah, so on the right-hand side, we are doing things a bit differently. So here we aren't throwing any exceptions. Instead, parsing the order, what it returns is a data type which might either be failure or success. Okay, so we are representing the concept of an error as a value, right? So here we are throwing an exception, which is a side effect. And on the right-hand side, we are once again limiting the side effects that might happen by representing the concept of an error as a value. So this has some consequences, right? We then feed this result that's obtained by parsing the order into validation. But validate order doesn't accept a result, it accepts an order, so we have to kind of unpack the result if it's successful and pass it to validate order, or just propagate the error. And that's what result.bind does. A similar thing with the mapping, we only want to apply the create invoice logic if there was no error before. And then we once again use function composition. So we compose the calculate total function with the apply discount function. They just do some pure computation without any side effects to calculate the discounts and the total, and we call the create invoice. So we've got a nice example of how function composition might look like in practice. So yeah, so here we've got imperative steps versus function composition and representing concepts as values. And finally, let's take a look at object-oriented programming, because I think that's also a very important distinction. So on the left-hand side, we can see some very classical object-oriented example where we have an interface with two implementations. These implementations have some private state, and they have some methods which are used to calculate an area of the shape based on this private state, right? So that's like classic object-oriented programming where we combine state and behavior. Now in functional languages, we often do something completely different. So we have on the right-hand side, that's Rust, we have we have an algebraic data type which enumerates all the possible cases that a shape can have. And the parameters there, the side and radius is kind of public, right? So we can unpack which we can peek into the if we have a shape, we can actually check what kind of shape is it, and then read the side or the radius. And then completely separately, we can have a function which calculates the area of the shape, right? So here the data and behavior are separate, right? So something that would be a crime in object-oriented programming, like anemic models, here is quite okay, and it's very often used. So we separately describe the data structure and separately define the logic, right? And that's this expression problem that's quite well known, because in one approach it's very easy to add new data types, in the other approach it's very easy to add new operations, and it's not really possible to have both in a practical way. Yeah, so object-oriented and functional actually have some differences, right? One is into how you represent state and behavior. In one case, it's combined. In the other, it's separate. But also in how you interact with the code, right? In object-oriented, like in very traditional object-oriented code, you are supposed to interact with your objects using message passing. So you send some message to an object, like call a method, and then the object somehow transforms itself in response to that method. So that kind of implies mutable data structures. It kind of applies mutability, right? On the FP side, you rather have composing functions as the main way of interacting with code. Okay, so we can summarize this into some traits of functional approach. So we can say that when we are using, for example, high-order functions and functions first-class values and immutable data structures, we are probably doing functional programming. On the other hand, if you have loops, if you are using a lot of statements, mutable data, that's probably not a functional approach, right? And we can push it, of course, further. We can have effect-free functions in the functional way, or we can have side effect functions that's like signals that it's more imperative. So that's kind of like a checklist of what a functional programming language or what a functional approach might be. Okay, so that was like the practical take. Now let's take a look at the theory. Like, are these somehow rooted in theory that's available in literature and online? Yeah, so of course our first attempt at defining functional programming might be to go to Wikipedia and just read the page, right? That might be what if you ask what functional programming is, that's what you would do probably, or ask ChatGPT. Will do that as well later. So in Wikipedia we can read that it's a paradigm where programs are constructed by applying and composing functions. Then there's a long article actually elaborating what they mean, but that's like the basic definition. And here we can see that like the main two traits that we have identified before are present here, so applying and composing functions. And this has some consequences, right? So if you want to construct your programs primarily by applying and composing functions, you kind of need to have functions as first-class values. So that's like a natural consequence of that. So then your program kind of becomes a tree of expressions where the results of the previous function applications are parameters to the next functions applications. But also, it's also required so that it's not only being able to apply and compose functions, because you can do that in almost any language, but it should kind of be the primary way to structure your code. Right, so that's the big difference, because you can probably apply and compose functions in C very easily. We probably wouldn't classify C as a functional programming language primarily, at least. So yeah, so it needs to be like the main your main approach there. But then this definition is okay, so we can go back to the definition over here. So yeah, so we apply and compose functions, right? But then you can wonder, like, what really is a function, right? So again, we can go to Wikipedia, and I think it's a good definition that a function in a programming language is a callable unit of software. It's something you can call many times. It's something that has a well-defined interface and a well-defined behavior. So you kind of know what to expect, right? And that's, I guess it's a reasonable description of a function if you write it in a programming language. But then there's also the mathematical definition, which is slightly different, right? It's a mapping between two sets, D and C, that for each element of the domain of the D set, there's exactly one value in the codomain that corresponds to that X, right? And such functions, they need to be deterministic, so for the same argument, you always get the same response and the same result. They also should be effect-free. So there are no, like, calling a function shouldn't cause the weather to change or the database to change or anything like that. So these are like competing definitions of functions, and depending which definition of a function you actually assume, you get very different flavors of functional programming. So if we assume the first one, I'm calling this casual functional programming. So it's a term I made up not long ago, so it's not very popular yet. And if you assume the second definition of a function, you get something that's called pure functional programming, right? You kind of forbid any kind of side effects to happen in your functions. And if you think about it, if you take the casual approach, right, that a function is just something that you can call many times. Well, okay, then, if you have a Java method, right, that's kind of a function. So doesn't then functional programming mean that we should simply have many small methods, or simply many methods which we combine? And to a certain degree, yes, that's like the first step in introducing functional programming to your code base. So yeah, so when you start with some spaghetti code, which is just a large blob of thousands of lines of code in a single file, then you can try to refactor it to extract some methods from it, make them small, composable, and maybe apply some other clean code principles. But then you can also, that's fine and that's a good thing in introducing clean code advice. But then there's also a lot of other things which you might introduce to actually reach the casual FP style, right? So we have all of these traits that we have identified before, like using higher order functions, which isn't necessarily something you do like in, let's say, old style Java, right? We might use algebraic data types. We might use immutable data. We might use an expression-oriented language, and so on and so on. So there's been a number of these traits. And there's like a huge difference between those two approaches. And then, of course, you can go to the limit and actually demand that all of your code has, all of your functions have completely no side effects and become a pure functional programmer. But that is also a big leap and one which doesn't necessarily have so much return of value. And to illustrate that, once again, some code snippets. So the left-hand side is kind of like the spaghetti code here. So maybe not spaghetti, but like old imperative code, right? So what we do is we have once again to parse even what this left-hand side snippet does. It requires quite a lot of mental effort. I think less. The middle snippet requires less mental effort, but maybe I'm biased. So yeah. So what happens in the left-hand side snippet? So we have an array of users. We have an array of people IDs. For each ID, we fetch a user from the database. Then for each user that we have fetched, we actually send a request to some remote service to ask like what kind of movies they like. And then we partition people into ones that like Star Wars and ones that don't like Star Wars, right? So that's the imperative version. And then we can refactor this code into kind of a casual functional programming variant where we take the people IDs array, we map this array by fetching from the database, we map once again by sending the request, and then we just partition. So I guess that's more readable. It's also totally not pure, right? Because the fetch from DB has side effects. The send request for obtaining the movies that a person likes has side effects, right? So it's not like pure functional programming. There are side effects in this code. But I think we have gained a lot when it comes to readability. Now, if we want to go this extra mile of purifying our functions and making sure that they have no side effects, we can go to the last code snippet, which actually represents any side effects as I/O values. And you can see that there's like this extra .traverse and this .flat map. So we need kind of to take care of this external layer of a data structure that represents computations. And I don't think it adds that much to the readability and maintainability of the code as this first transformation does. This last code snippet, like it has some advantages. For example, refactoring might be safer and you might do it with more confidence. But I think the majority of the value that you get is this first transformation over here. And actually, I'm not alone in this view. There's a quite well-known talk from Jane Street. Jane Street is a financial company from New York. They make a lot of money on the stock market, and they do so using OCaml. OCaml is a functional programming language. I think Jane Street is the biggest commercial user of OCaml. They have all of at least majority of their software written in OCaml. One of the programmers there made the talk, why functional programming doesn't matter. Of course, it's a title that's supposed to catch your attention, clickbait, because he says why it does matter in the talk. And he like identifies 3 things why functional programming is good for them. And these are dexterity, meaning that they get static type verification. OCaml is a statically verified programming language that they can have data structures where you can't represent illegal states. Performance is important for them because in OCaml you have a very predictable way of translating this functional code into machine code, so they can understand like what works and when, and how fast. Yeah, and correctness. Sorry, so that's the ADT point. And for correctness, once again, static types here help them verify things at compile time. What they don't mention in the talk is that purity or lazy evaluation is important, right? So they rather focus on the other traits of functional programming that we have identified, not on limiting, not necessarily on limiting side effects. So it's an interesting talk. I think it takes like 20 minutes. 25 actually. If you're interested, you can take a look. And I think one of the reasons why going 100% pure isn't really that important is because shared mutable state is always there. Like it's great if you can limit it in your code base locally, right? It's great if you can eliminate it, right? It's very hard. It's just an opportunity for bugs. But in the end, we have to keep in mind that however hard we will try in our local code base, globally, the world is mutable, right? If we have two threads of fibers, one which writes to the database with a user update, and the second which reads from the database, the same user, there's still the question of which one will complete first, right? So our code might be functional, it might be imperative, it might be whatever. Like whatever approach we take, this shared mutable state is there, right? Or when we call an external service. So, whatever your approach, this complexity is always going to be there. Okay, so some other definitions of functional programming. The right one actually is quite interesting. If it's correct, of course, because you can never totally trust Stack Overflow. But if it's correct, historically, it says that the first definition of functional programming came from Lisp, and it focused on capturing functions as first-class values. Only later, Haskell came in and kind of reformulated the definition of FP to be more focused on limiting side effects and limiting mutation. So this would kind of correspond to our distinction between casual and pure functional programming. And then there's this paper, which is, I guess, the classic, you might say, definition of FP by John Hughes, Why Functional Programming Matters. So actually, this talk is kind of a response to this paper, but 20 years later. So if you want like an academic definition, the paper says that functional programming is so called because its fundamental operation is the application of functions to arguments. Then it later defines functions as the mathematical kind. So it more like talks about pure FP. So in the academic terms, at least, FP would be probably the pure variant. And the paper defines lazy evaluation as kind of a new glue comparable to eliminating GoTo, which allows you to create modular programs and lazy evaluation. And finally, on Reddit, you can always count on Reddit. One answer I particularly like is that what even is functional programming, and the answer is it's a vibe. So it's something you have to, feel in a way. I guess that's what we've been trying to do by comparing these code snippets to actually get a feel what functional programming is. But then it follows that in the quite, I guess, good intuition as well, that an FP language is one in which it will be hard or impossible to do ordinary easy things without using functions, right? So it focuses on this ergonomic aspect of how we can actually use functions in our languages. And yeah, you might also associate functional programming with Haskell. And we can just go to Haskell's website and see what they say about functional programming. So as expected, they kind of focus on avoiding mutable state, on avoiding changing global state. So that's the same idea as in pure FP. So we might try to formulate kind of our intuition what functional programming actually is. So what does it mean in the practical terms, right? So when somebody says to you that I'm doing functional programming, what they probably mean is they write their code in a language where applying, composing functions, using higher order functions, capturing functions as first-class values is ergonomic. So it's not just possible, right? Because you can do it in C as well. You can capture a function as a first-class value. It's not that ergonomic. In other languages, probably like it was very unergonomic in Java, but then they introduced lambdas, and now it's much better, right? So yeah, so it needs to be done in an ergonomic way, so the language needs to support it. But then there's also all these techniques that actually make an approach functional, right? Such as using algebraic data types, using immutable data structures, having all the programming language constructs be expressions. So a very good test is if a conditional statement is an expression or not, avoiding shared mutable state, representing concepts as values. So maybe not representing all effects as values, but at least some, such as representing error states as values. This might be actually much better and much more easy to comprehend when you read the code than throwing exceptions, because exceptions kind of have these non-local effects. And we also have this separation between data and behavior, which is like in contrast with object-oriented programming. Yeah, so a function programming language would be one where all of these can be done ergonomically, and where this is also actually used, right? So this should be witnessed by the standard library, the external libraries should use functional approach, and the documentation, right? So it's not just that you can do all those things. Like for example in Java, you can do immutable data structures, but actually most of the libraries, most of the standard library, the external ones as well, actually use mutable ones. So that probably wouldn't be a good fit here, right? So functional programming must simply be the dominant way of constructing programs. So yeah, so now let's take a look at how functional the languages that we use actually might be. So I've prepared kind of a scorecard. You might, of course, disagree with it. You might tweak it. It's like online somewhere, so there's like a spreadsheet. You can make your own scorecard if you think I'm wrong somewhere. Yeah, so let's actually start with Java, right? So we have a couple of these characteristics here which we have defined. So some, for example, functions as first-class values, as I mentioned, you can represent them in Java in a quite nice way with a pretty low syntax overhead. It's much better than it used to be. So Java is not that expression-oriented. For example, the if, right, is a statement. The standard library is completely non-functional. It's just, well, Java focuses on compatibility, right? So it kind of cannot change the standard library without breaking that. So we are kind of stuck with hash maps and array lists, which are mutable and not really that functional. And the APIs are kind of imperative as well. So no points here, unfortunately. Yeah, so what about actually your approach to writing code, right? Well, typical Java code doesn't really focus that much on applying and composing functions. Once again, it's more like it is possible to write it in functional style. It's not the dominant way. You can create immutable data structures like records. You can have pattern. Well, you do have pattern matching, but it's not that widely used. Like it's just a possibility as one variant that's not the mainstream one. And you don't really represent effects as values. So the score here is quite low. So let's now look at Kotlin. Well, in Kotlin, you have very lightweight syntax for representing functions as values. The language itself is much more expression-oriented. The standard library is somewhat functional, so we get some more points here. Immutable data structures, they are more pervasive, but still Kotlin focuses on compatibility with Java. It is kind of like a better Java, right? So like the default collections in Kotlin are still mutable, so their usage will be still quite imperative. You don't really represent effects as values as well, right? You just use you just use exceptions. You don't separate data and behavior because it's more like an object-oriented language. So So the score here is a bit higher, but still not that high. So now let's take a look at Scala. Since Scala is like one area where I've spent a lot of time with, I'm actually I will show you two variants of Scala. So one is a very functional, a very purely functional approach to Scala using libraries such as Katz effect or Zio. So these are libraries which help you write purely functional code, so where your functions don't have any side effects, and this scores quite highly, right? Scala itself as a language lends itself very nicely to writing functional code. So the syntax for defining functions as values is very lightweight. Almost everything is an expression in Scala. The standard library is functional. So the entire Scala standard library is based on immutable collections, on higher order functions. So this like quite this like separates it from Java and from Kotlin quite clearly. You very often use immutable data structures like case classes, this like data classes in Kotlin or records in Java. So that's like the default way of representing data in Scala. In the pure function approach, you try to limit effect. You try to eliminate any effects. Of course, you can still cheat. So no full points here. And very often you separate the behavior and data, but not always, since it's a hybrid language. But we can also use like vanilla Scala, which is like, let's say, an everyday subset of Scala, where you still have the same language, which is still quite functional. You don't represent effects as values as often. So if you remember these three snippets where we've compared various degrees of functionfulness, something like that. This would be like the middle one. So there's a bit less points here, but still quite high in the scorecard. Of course, we have Haskell. Haskell scores almost the highest score everywhere, except that it's still possible to cheat, right? You still can, even if you you represent all of your computations as pure functions, you never know. You can still cheat somewhere deep down and just write and just run a side effect using unsafe perform IO. So I don't think there's actually any language that would be in any way commercially used, at least, that allows you to verify that the function is pure. So that might be because of two reasons. Maybe it's just too hard to verify, or maybe it's just not that important. And finally, we've got Rust. So Rust might seem like an unlikely contender in being a functional language, but it's actually much more functional than you would think. So we have light syntax for defining functions as first-class values. Rust, the control flow operations in Rust are expressions. So you can assign values basing on the results of the usage. The standard library is quite functional, so all the collections. So the approach here is a bit different. So you don't get immutable data structures. Instead, you are using the borrow checker to verify who owns a particular memory area. So the method is completely different, but the result is the same in that you avoid global or shared mutable state, right? So in Scala, in Kotlin, and Java, you can avoid shared mutable state by just using immutable data structures. In Rust, you have mutable data structures, but you don't have the shared mutable state because the compiler verifies that only one point in code at a time can access or modify some state. So that's like a different mechanism, but same outcome. So the no shared mutable state quite high here. Behavior and data are separate. So in Rust, you don't get any object-oriented things, so you cannot really combine data and behavior. You do have those enums and these algebraic data types, which are like the default way of modeling your data. So Rust takes a different approach. for example, to managing memory, right? But overall, it is quite functional. So all the collections, for example, that's also an important thing. All the operations on collections are usually done using .map, .filter, so the things that you would know from a functional language. They are compiled down to efficient machine code still, using some, because generics and collections in Rust work a bit differently. But when you write the code, you use it very similarly as you would doing like functional transformations of collections. So yeah, so these are the results. We've got, Haskell on the right-hand side, which is the purely functional programming language, Java on the left-hand side, which is, I guess, still quite, despite the recent additions, a rather imperative one. And then we have all those variants in the middle, which I think might capture what's best from a functional, from the functional approach. Okay, so now concluding. First of all, if you have, maybe now you have some questions, so you can go and ask them. So you might take the checklist and wonder if you are more of a casual or of a pure functional programmer, or you are maybe not into functional programming at all. That's of course fine. There's a couple of must-haves that the functional programming language must have. Well, yeah. So it's composing functions. It's a light syntax for representing functions as values and for higher-order functions. There's a couple of nice-to-haves, like immutable data types, ADTs, being expression-oriented, representing concepts as values. But what I guess is important is that purity is not on that list, especially not on that list of must-have, right? At some point, FP actually starts to provide diminishing returns, right? If you can go purely functional, that's great. But I would argue that most of the value that FP brings is in the casual variant. So it's in all the other things that we have listed. And we have a lot of great languages, actually, both on the JVM and outside the JVM, where we have these functional programming concepts baked in, and where they are made ergonomic and practical through the language, through the standard library. So, go out and explore what fits best. And finally, I would like to mention my company where I'm working. We are a software consultancy, a software house. We try to solve all the hard problems that our clients face using software. So we very often work on the back end, either working on performance problems, on making code or applications more scalable, more distributed or distributed at all. We have a lot of job openings in Java, in Scala, in Kotlin, TypeScript, Rust, and probably some other data science as well. We are part of Virtus Lab group. So these two companies form a group, and we work together. So if you would maybe be interested, take a look at our site for either the job openings or our technical blog, which is quite popular. And that's all I had. So thank you. Now I'll go and check if there are any questions. OK. What about Clojure? It has 70 out of 65 points. OK, I'm not an expert of Clojure. You can go, there's like a blog. It has a link to the spreadsheet, so you can create this, fill in that spreadsheet for Clojure and send me the results. I will amend it. I think Clojure would have 70 points out of 65. Probably not. I don't think. I'm not sure how Clojure is behaving when it comes to purity. I don't think it requires any form of purity. It doesn't require static types, right? So, and I'm pretty sure it doesn't trace purity as well. So that's one area for sure where it wouldn't get the maximum points. OK, throwing an exception is a side effect, not in Java. Throwing checked exception is part of method signature. It has to be handled by the caller, var FP. Yes, that is true. So exceptions, kind of the checked exceptions in Java, you can take the viewpoint that checked exceptions are actually another syntax for returning either failure or a result in Java. So yeah, that's a good remark that unchecked exceptions are a side effect. There is a very interesting thread on Stack Overflow on what is actually wrong with exceptions, and that's one of the points that's listed there, that checked and unchecked exceptions are actually totally different beasts, and that the checked ones actually can be considered syntax for returning either's. Where would Golang fall on this scale? I don't know. I only did toy examples in Golang. I don't think it would be that functional. I mean, can you even do higher order functions there? Like when you have collections, do you even do that in Golang? I'm not sure. So once again, I would be happy to amend this this chart with languages that are outside my area of expertise. Do you consider Lisp style FP with mutable state dead today? Well, I'm not sure if Lisp is dead. Like people are using Lisp. Maybe it never went mainstream, right? I think we have to consider it FP because it's kind of the first FP language out there, even if only because that you can represent functions as data. That's like in Lisp everything is data, right? So maybe it wouldn't like score highly with the mutability, but on the other areas it's probably very FP. Is modularity a thing in FP? Do you encapsulate anything? Group. Okay, I don't understand the group thing. Yes, of course it's a thing in FP. I guess you just modularize it differently. So in Occam, for example, you have the distinction between signatures and between implementations, and a signature is like the public interface, the implementation is where all the private things sit. In Scala, you have the traditional modifiers that you have in Java, which are a bit enhanced. So you can, for example, scope things only to a package, and you typically only expose a small set of functions or a small set of data types. So yeah, of course, modularity is a thing, and yeah, you do encapsulate, but using a different mechanism. In which practical cases is it worth to use FP in Java, in your opinion? Well, for sure, for collection transformations, I guess it makes code much easier to read. And I guess you can use really as long as it's, if you can use immutable data structures inside your code base, that's great. You will already win a lot and gain a lot of value. So it's just that, on the edges where you have to integrate with other libraries, you will still have to translate between mutable and immutable data structures, or collections, for example. So there will be some friction. So I'm not saying don't use it. It just will be a bit harder than in other languages. And yeah, no lambdas in Java 6. I guess in Java 6, I guess it's more of a statement than a question. So okay. So thank you very much. I hope you enjoyed it. And if you have any other questions, I'm here for the rest of the conference. Thank you.